Yeah, good afternoon, everyone. My name is Ying Gao. I'm from MXV Rail, or M times V, because we just changed our name in March. And so this is the new name, MXV Rail, and we're formerly TTCI. Bear with me with another broken spike topic. We already have three in this session. So my topic is about the investigation of spike breakage at fast and in revenue service. So we focus on get the loading environment of the spikes actually seen in the in-track. So thank you for Marcus and Christian's introduction on the spike failure background. So I can quickly talk about the problem statement and objectives, and then I'll focus on some preliminary modeling results, and then a field investigation using instrumented spikes. So we'll have one revenue service testing using instrumented spikes and two tests at FAST. FAST stands for Facilities for Accelerated Service Testing, located at Pueblo, Colorado. And based on the field testing, we get the loading environment of the spikes, and based on that, we can calculate the fatigue life of spikes. And the last one under this bullet is the identification of a broken spike using ultrasonic testing. I will briefly talk about one project that came through from the FRA support. And last two bullets are summary and the future work. So broken spikes typically happen on elastic fasteners, especially on the high rail. Historically, this problem is observed at fast and revenue service. So at fast, it has a 6-degree curve, and we typically run 115, 315 Capes cars. So it's a little bit higher than the normal railroad operation. And we also observe this issue at revenue service, and as Marcus and Christian mentioned earlier. And this is not only a cut spike issue, it happened on drive spikes and lag screws as well. We believe this broken spike issue is a fatigue failure. As you can see here, normally we look at the failure plane of the spike. The initiation of the crack start at the corner of the spike, and then you can see the fatigue ring, and then propagate, and somewhere here, and then the entire spike snap. And then we also see some fretting and wear between the spike and the plate area. So that means that a lot of interaction between the plate hole and the spikes. The loading environment that the previous presenter mentioned several times. So it can be a combination of the dynamic train loads laterally and vertically, and it also comes from some longitudinal load from the braking and the tracking and the thermal forces as well. And the bottom right plot here shows where the typical break point is, about 1 to 1.5 inches below the surface of a cross tie. So it's very hard to identify. So in order to get the loading environment of spikes that is actually seen in track, we developed this instrumented spikes. The idea of instrumented spikes is actually from Norfolk Southern back in like a couple of decades ago. What we have done is we put string gauges at where the typical spike failure occurs on the fore surface of spike shafts. So in this way, we can measure the longitudinal string and the lateral string on the same spike. And as you can see here, there are two locations where the string gauges are. So this one is a little bit close to the head of the spike, and this spike is a little bit longer to the spike head. That's string gauge location was determined by the field observation and the modeling results. I will talk about that later. So based on the reason of these two locations is because the plate has a thickness. So if you at the rail spike location, it will occur actually deeper from the spike head. If you locate at the anchor spike location, then the spike failure plane will closer to the head of the spike. And what instrumented spikes can tell us? So it will give us the loading level of the spikes, and it will tell us how the load distributed among the plate and along the track as well. And also it will tell us what the effect of the spike position. So there's a tolerance between the spike plate hole and the spike. So the spike can be anywhere in a spike hole. So I will show that later. And based on this loading environment of spikes, we can estimate the fatigue life of the spikes. And last one can help us to evaluate what remediation methods are effective. So first, the revenue service testing, I'll give some background of the test location. This test location was at Danny Curve, Pennsylvania. We conducted this test in 2018. It is a 8.4 degree curve with 2% grade. And the main one is mostly had loaded and downhill traffic, and main three mostly had empty and uphill traffic. The train speed here was about 10 to 50 miles per hour is under the balance speed. And we don't have many instruments spiked at that time, so we only instrumented one high rail plate per track.
A little louder, please.
Sorry. Okay. It's better? Okay. Thanks. I couldn't hear. This spiking pattern is 4 spikes per plate, and the 2 rail spikes and the 2 anchor spikes I can see here. And the fast testing environment is the 6-degree curve with only 0.2% grade. And we have 2 locomotives and 45 cars in this case. And the operation speed was 40 miles per hour. It's overbalanced speed for this track. And this location, we have 3 spikes per plate, and they're all anchor spikes. So based on this fast testing and the revenue service testing, we get the loading level in the spikes. This is within our expectation. As you can see, we normally consider 1500 microstrain is the spike material fatigue limit, and which is depicted by the dashed red line here. As you can see, some of the spikes under some wheel load exceeded the 1500 microstrain. So we believe the fatigue failure is a mechanism. And more than the exceeding of fatigue limit, we also found some permanent strain within the spike. As you can see, at the first lap, it started at 0 strain, but there is a jump in the strain. It's jumped from 0.000 to approximately about 0.001 strain, and it will never come back. So there's some permanent strain, permanent bending within the spike. So after 7 laps in the same direction, as you can see, the permanent strain is already in the spike and is stabilized there. And that's the one direction of the train. If we change the direction of the train to the other direction, we will see some disturbance in the spike. As this is the flow of these four plots here. So the first one, at the first lap, we can see some permanent strain going on, and then the last lap, when it's running counterclockwise, is stabilized. But once we change the train direction, the permanent strain start to build up again. And then after several laps clockwise, then it is stabilized again. So a permanent strain will initiate some micro cracking in the spikes, and it will definitely reduce the fatigue life of spikes. So other than the loading strain level, we also investigate the distribution of the bending strain in spikes. This table here shows the spike on one plate. So this plate had 3 spikes and was tested at fast. As you can see, in the lateral direction, one spike was taking about over 60% of the load that's transferred into this plate. And in the longitudinal direction, there are 78% of the load transferred in this plate in the longitudinal direction. So this tells us the majority load was taken just by the one spike on the same plate. So the load distribution was not even. So we conduct a model to evaluate what's the effect of this uneven distribution. So the first case is the spike is perfectly sitting in a spike hole. The red, the outside box is the plate hole, and the inside, the gray square is the cut spike. And the second one is if one edge touching the spike, the plate hole, and the last one is once it has 2 edges contacting the plate hole. And within these 3 different positions of the spikes in the plate hole, we can see there's a significant difference in the stress level in spikes. So the last case, we identify a 275 megapascal, which is about 40 KSI stress in the spike. It's already exceeding the fatigue limit. So this is a photo this is a video to show this phenomenon. So look at there are 2 spikes on this side of the plate. Look at the front one, how it moved. Yeah, there's 2 reference lines here. So the front one was moving when the train was running on it. Let's look again. And on the same plate, the spike in the back was stationary. So that means the front spike was seeing more deformation, possibly higher stress than the other spikes on that plate. So in order to find some remediation methods and evaluate how effective they are, we conduct this field testing at FAST and on different fastening systems. We have case 1, that's the 18-inch elastic fastener with cut spikes and it's anchored. And case 2 is the same plates and the same spikes, but it's non-anchored situation. And case 3 is a curved block plate with cut spikes, and the entire section was anchored. The curved block was only installed every 3rd tie in that area and intermixed with standard ARIMA plate. So the last one is the ARIMA 16-inch plate with cut spikes that's anchored track. So with these 4 cases, we try to understand what's the loading environment difference in these 4 cases. And the case 2 and so case 1 and the case 3 were considered as the 2 remediation methods that railroads would like to test. The analysis we have done with the data is to look at a peak-to-peak difference of the strain gauge level. So this is peak-to-peak strain gauge difference is defined by when the train wheels is right on that spike, what's the highest string level the spikes is seeing. And once in between trucks, and then back to zero of the string level. So that this is the peak here to the peak here at the bottom, that's considered as the peak-to-peak string. And this is indicates what's the dynamic train forces actually affect the spike string level. So as you can see here, case 1 to case 4 in the lateral direction, most of the microstring was below 1500. That means the majority of the spike load that they are seeing are actually below the fatigue limit. However, you can see here for case 1 and the case 3, they're about 1.6 and 6.2% that are between 1500 to 2000. 2000 is typically considered as the yield point, which will cause some permanent bending in spikes. And the case 2 has the highest percentage when when the strain gauge level was above 2000 microstring. We're working on the fatigue analysis using this string level. We believe this 4.5% will significantly reduce the fatigue life of the spikes, but we have not confirmed that yet. The average strain is listed here as well. As you can see, in the lateral direction, case 2 had the highest average strain level as well. And in the longitudinal direction, case 2 had the highest as well. That shows the real anchors really help to undertake on longitudinal load as well as possibly some of the lateral load as well. So this is the handheld ultrasonic testing we have done for broken spike detection. The research was supported by the FRA. We have tested both single element and the dual element transducers, and with different frequencies and diameters and the roof angle, which is the properties of the transducers that are used to detect broken spikes. With the field testing, we did a blinding test. We conducted on both cut spikes and drive and screw spikes. Only the cut spike detection was successfully reported and with no error. However, for drive spike and the screw spikes, according to their complicated shape and there are some indentation on top of the spikes, it's very hard to use ultrasonic testing to detect where the failure plane is in track. So, but this test definitely give us some confidence in ultrasonic testing because it can report the cut spike detection successfully, and it could lead some other research to help us to have some automated broken spike detection, because we have this handheld UT already confirmed the spike detection can be feasible. So to summarize my presentation, the first, the load taken by the spikes could be high enough to cause fatigue cracking and even permanent bending. And the second is the field test result shows the broken spikes is a result from the longitudinal load and the lateral load as well. And the load environment in the spikes on the same plate was not evenly distributed. This could lead to kind of the virus effect. Once one spike is broken, and the load will transfer to the other spikes on the same plate and cause the sequential breaking on spikes. And also, we based on the faster test, we installing real anchors for elastic fasteners. We're using curve block plates could reduce the spike load level. And lastly, we test the handheld ultrasonic testing method, and it was successfully detect the broken cut spikes. For the future work, we will continue to monitor the in-track performance of the spike conditions on different fastening system. So remember the case 1 and case 3 were two remediation methods that we are testing. They accumulate about 340 mGT so far. We haven't seen any broken spikes yet. However, the elastic fasteners without rail anchors start to have broken spikes in 200 mGT. So it broke sooner than the other two remediation methods that we are testing right now. The fatigue analysis, we would like to perform this to estimate the spike service life in different fastening systems using the instrumented spikes data. We may not have a silver bullet to solve the broken spike issue, but if we can elongate the spike service level to a certain point, then when the rail gang or tie gang come here, they can start to change out the spikes without having breakage in that track before they come here. So that's our goal to help railroad to elongate the spike service life. And for this work, we'd like to thank the FRA's support and the AAR support as well. And I would like to thank the test support from Norfolk Southern. And my contact information is there. Feel free to contact me if you have any questions. Thank you.
Questions for Dr. Gauss? Again, thank you. Question about the test train when you have instruments like
we just have two in the front.
Two on your test train?
Yes. So for the yes. We have two locomotives and 45 cars because I would like to change direction during the testing. So we just run this during the day. So have a shorter train running. Just on one end. Yeah.
I'm hung up on the fact that you're running open balance here. Seeing the failure.
So I think both, so the 40 miles per hour is the overbalance speed. We have seen in both situations, either it's under balance speed or over balance speed, the spike will see a loading environment higher than the fatigue limit. So.
You're in the same section 25.
Yes. High rail only. Yes. Yes. Yeah. So this fastening seams start to have broken spike around 200 mGT, and once we put some anchors on, it lasts longer.
Any other questions?
Yeah, sir. Just for this test, yeah. So the spiking pattern was a 3 spike per plate. That's the original spiking pattern. So that's why we removed 3 and replaced with 3 instrumented spikes. Yes, it's a 18-inch plate. So.
Pre-drill when you spike them?
No, we did not. So because we just pull out the existing spike and replace with the instrumented spike. We did not use wood plugs either, because we don't want the compressive force to damage the gauges. So. Any?
Go back to the picture of the broken spike. Well, there was one where it showed across right here.
This one?
Yeah, that's right there. So it's sheared. So. Any other questions, comments?